Over to you. Thank you.
Amazing. So hopefully you can all see the slides I've shared. So my plan for this talk is that I'm gonna go through from the motivations to my research to what I'm actually doing and some of the findings from it. Feel free to jump in at any time with questions, and we'll just see which rabbit hole we end up down. Like this for me is trying to get 2 years of research into what I'm aiming for is half an hour of talking. So I've been deliberately vague in places, so please jump in if you want things clarifying. So we're going to start with what contrastive training is. And if you think to, I don't know how familiar people are in this room with computer vision, but a big part of computer vision is the ability to see an item and sort according to what that item is. And you think of the problems that that gives, such as I can recognize that I'm looking at a computer screen, as I imagine many of you are, and yet you might also classify it as looking at a presentation. And depending on what I'm doing in this presentation, you might go, oh, well, there's a human there, there's a slide. And yet these all exist in the same visual space. Now, this got solved a couple of years back now by something called CLIP, which is this diagram in the top right, where essentially what I've labeled as L and I are a language input and a image input. And what CLIP does is you've got two encoders, one for language, one for image, and it trains those representations to each other with cosine similarity. Now, what this means is that there is no supervision for labels. All the computer gets is a language prompt that matches a given image in the set, and it learns to emphasize the correlation between that input of image and that input of language over all the other inputs of image and language. So this built on work with visual semantic embeddings, devise, and something in the computer vision space called GLOM, which are the previous works to this, which look at doing multi-level image processing. Whereas the power of CLIP, insofar as being the backbone that's gone on to train models that you might recognize, such as DALL-E, and I think it's even used in Stable Diffusion still. This model learned a level of computer vision that otherwise did not exist before it. And the power, essentially, is that because you're not telling it what to look for, but just going, does it match or doesn't it, you get a much broader set of interpretation. One of the early papers that came out from this was talking about what's quite confusingly called multimodal activations, i.e. that the model can learn the logo of something as meaning the same as the actual thing. So you could show it, say, the act that plays Spider-Man and the Spider-Man logo, and it would get the same activations, which is quite exciting, because at the time it was thought that only humans had this ability. So that's what CLIP is as a start. However, as this applies to our traditional language training, which you'll recognize in the bottom left, where you've got a language in and a language out, and usually this would be a masked input, so you're learning what the tokens do. And then you compare your output to your ground truth, and hopefully that loss guides your selection. The problems, as many of us may know with this very basic pipeline, is that the individual tokens you're predicting are they're very prescriptive of a model. So if you get a token wrong, you are just objectively wrong. And whilst you can emphasize the correct one in your training, and that's what the gradient process does, you don't get the semantics carrying through. So if you've got a near miss, for example, if you're doing a question answering task and the answer it wanted was yes, and your model output yeah, you'd be marked wrong, and yet the semantics are correct of what you're saying. So this prompted a early foray into trying to use images to guide that gradient. So what you can see in the bottom right of this slide is an approach that splices CLIP into that pipeline, where instead of using a ground truth language, we're using a ground truth image. And you'd use this pre-trained model to say, actually, if I've got a language input and a language output, I'm then re-encoding that output into the clip framework and comparing that to the image. So the idea being that prompts that are semantically similar would hit off on this multimodal activation within the clip model, and you'd get the correct output. So there's a few problems with this approach. The biggest one in trying to implement it is that the language that comes out of an encoder is not the same as the language that can go into a clip pre-trained model. There are tokenization problems, and at a basic level, this can just be it's a different encoder, words not the same, tokens aren't the same. But as you dig into that, the scheme of encoding is really important, especially when you start considering problems around low resource language. So in a low resource language, the chance of your tokens being the same as in any other language is really slim, yet alone then the problems that exist trying to do that conversion between different models while preserving a gradient. If we go back to this slide, this conversion of language out to L does not always preserve a gradient, because you can go, well, I can convert language out to English or whichever language you're using, and I can then retokenize it, right? But as you then try and train that model, this loss of gradient means that the loss function that exists with cross entropy loss here does not carry back into the encoder you're trying to train. And there's a lot of research that's gone into, oh yeah, this doesn't work. So feel free to ask me about that at some point in the future. However, here's the next part of where this took me. So the idea is that instead of what you'll recognize in the center of this as, again, the same clip model, but using our second language encoder to add an extra dimension to these logits. So in a clip model, where you'd normally take the diagonal of this contrastive training and emphasize it, instead, we're now taking the diagonal of a cube and trying to emphasize it. So ideally, our three inputs this time are ground truth, output, language, an image, and now another language are all correlated. And if we know that, then this training for all three encoders should work well. And we can even use a pre-trained encoder for English if we've got those as inputs that fit. So in 3 dimensions, in the bottom right of this slide, you'll see what this looks like in practice. You can see a white square on the bottom left of this cube and on the top right. And that is where the diagonal that's going through the cube, those are the items that exists for in each batch. However, you'll also notice on this cube that other items are not uniform. So the squares along the edges, where you can see a slight faint diagonal, those are a light grey, because for those items, they share at least 2 or more similar coordinates. So you can see that on this front face, there is a light diagonal that goes 1, 1, 2, 2, 3, 3, 4, 4, and so on through that cube. And the edges on row 0 corresponds to the top squares row 0 as well. So the idea behind this is that we've got certain points in this cube where we're expecting a better correlation but not perfect. And my research is looking at whether that's actually useful for training a model. And the fun of this is that this approach scales up into 4 dimensions and 5 dimensions and 6 dimensions. So in the top right, we have a representation of what this looks like in 4 dimensions, plotted as a square of squares to try and get those 4 dimensions mapped on. So you can see going down the diagonal top left to bottom right, the sort of smaller squares in that each have a white spot in, and that corresponds to the same diagonal through a 4-dimensional cube. I was struggling to plot this for 5 and 6 dimensions because I just do not know how to visualize that in a way I can easily convey. But we'll get on to how and why that works. So the applications of this approach are several in that, firstly, we can use pre-trained models as guiding of other logics for other encoders. So you could say that actually, if I believe in universal language theory, I know that an encoder such as clips that nicely maps onto things like if I can assume that an encoder represents all English interpretation as is visually grounded, and I know that other languages have that subset, I can assume that using my pre-trained model can easily guide these other encoders. And so you could implement this with a second optimizer in training or an additional loss metric as weighted. And I've tried both of them at various times, and they work to varying degrees depending on the method I've used. So before I go on, I'm going to talk a little bit about evaluation for this, because this is where stuff gets interesting. You'll notice that in this model, there's no decoders and there's no ground truth going in terms of there's no output that is human readable, is what I mean by that. So I can't just compare it token by token to something that I know is correct, which poses some interesting problems for evaluation. So one of the first approaches that I looked at implementing is this, which you'll see as this graph, VIT base versus ResNet. And this lovely heat map represents the activation through the layers of each model. And what it's showing is that early in the model, the layers roughly are a better match to layers earlier in the other model, which is where you have this nice diagonal glow through it. And the fact that one is a transformer and one is a convolutional network, if I'm not mistaken, is borne out in this quite grid-like structure, where both of them have a either convolutional or key query answer set of layers, and therefore both have these sort of regular vertical and horizontal lines that match. However, if I compare this to my training, and you'll see the all black and all pink graphs that have been produced, I have some differences there, not gonna lie, and it just hasn't worked. And part of this problem is that because of how expensive centralized kernel alignment is to use in training, where you're looking at, to get it a meaningful approximation, something like 10,000 samples, and you're logging every single weight that your model is producing for every single step across the entire model, then performing mathematical reductions on that. I've had to take some shortcuts in the code, and I've tested every single one of these to show that they're doing exactly the same mathematical function, and yet I'm still getting this result. So I'm 99% sure it's not an error in code. What I can infer, though, is that my weights of my model are just fundamentally different to those in the stock clip model, which is what I'm comparing against. So in light of this, I've used linear probes. And a linear probe, or linear regression probe, as it's sometimes referred to, is where you take the representations generated at each layer and you pass that through a linear regression, and you basically just record the best output you can get. So you'll see here this text probe that I've got from one of my models, where you can see as training goes forward, the predictor of the text encoder and how good it is at picking just the best class for an image increases as training progresses. And in the original clip paper, they use these, showing that after about 33 GPU years, they get a good result, which is obviously something I think I can improve upon. And just for a good comparison to that paper, I've also used a validation loss, which is using their stock method, hence the name of that graph. And that's looking at if I was just using one language input and one image with the same model as, or sorry, same method as originally proposed in the clip paper, but with my own trained encoders, what does the loss look like? So I'd expect that to start to dip quite early and come out around 0.1, 0.2, which is what normal pre-trained OpenAI version of Clip gets to with the same dataset as I'm using. So the theory that I'm going to be evaluating is how well the logics in a model track to performance. One of the big breakthroughs of CLIP is the idea of in-batch negatives. So depending on your NLP background, you may be familiar with the term in-batch negatives. And usually in an NLP context, it follows mapping inputs with a label of is this correct or is it wrong, and starting to teach a model to predict how good or how bad the answer will be and know whether it's right or wrong about something. Whereas the way that CLIP is trained means that every item in the batch that does not correlate between the two inputs are used as in-batch negatives. And what this really means is that you're sort of slave to the hardware that you have in terms of scaling laws. So if you think about a grid of 64 by 64, you've got 64 good samples in there and 64 squared total samples. Whereas if you're able to scale your batch size up, your ratio suddenly gets an awful lot better. The theory behind what I'm doing is to say that actually, if I go back to the picture of this cube, the volume of that cube compared to the diagonal is now so much better than just the square of a face. And so my expectation would be that the number of logics that I've suddenly got there being batch cubed compared to the diagonal, which is still length of batch size, that ratio just gets better and better and better. So I'd expect training to be better. So that's one thing that I'm aiming to test out. Another problem that I have is that the behaviors beyond 3 dimensions start to get really interesting. And the graphs that I've got on this slide are a slight insight into that. So with 2 dimensions, you either have the coordinates of the item in each batch or the index. They either match or they don't. You have 2 set behaviors. There's one thing you're maximizing and one thing you're minimizing. Whereas when you get to 3 dimensions, as I briefly talked about, you have 3 behaviors. You have they either all match, they either all don't, or there's a partial match in there. Whereas when we get to 4 and 5 and 6 dimensions, this gets murky. So you can see on this graph that we saw earlier of what 4 dimensions looks like, there's actually quite a few different colors in there. And that's because you have a match of all of them, a match of none of them, a set where 2 coordinates match and the other 2 don't, or where 2 coordinates match and the other 2 match each other as well. And then you've got a set of 3 and 1 as well. So what you find is that actually, as you start to make this cube more dimensions, the number of distinct regions that have to be modeled increases. And these graphs in the bottom right model exactly what the proportion as volume of that cube each region represents. And you can see that as the number of dimensions n, which is on the bottom axis, increases, the mean proportion goes down. However, when plotted by batch size, which is the bottom graph, there are some funky behaviors in there too. For example, if you imagine the extreme cases where you have a cube of size 1, you only have 1 and then nothing, and same in 2 and 3 and 4. And if you scale this up to a cube of, for example, an infinite size, actually then the volume of coordinates that match no other coordinate tends to infinity compared to all the other factors. So that's one of the avenues of research that I'm actually pushing as well. So I'm going to move on to look at some experiments that I've gone into, which, as I've already slightly hinted at, are looking at what happens as you start to scale these logics into more dimensions. So we've talked about region explosion. Another phenomena that I've looked into are something called James Stein estimators. And this is a quirk that emerges after 3-dimensional space, where if you took a value, just randomly sampling a space, in fact, I'll change to a blank slide and we'll model this. So if you have a normal distribution like that, and you're told that this central value is mu, if you're given a random sample from this distribution, let's say you're given this value here, the assumption is, based on a single sample, if you don't know what this value is, then that is your best estimator. If you're talking in 2 dimensions, where say you've got a normal distribution going this way as well, if you excuse the really awful drawing, and you're given a y value to estimate this average, then what you'd normally say is that your first estimate and your second estimate are your best estimators for those intermediate values. However, if we add a 3rd dimension to this graph, going that way, then if we had a 3rd value on there, those 3 values are no longer the best estimate for a coordinate that represents all 3 means in this space. And as you add 4 and 5 dimensions, that becomes more and more accentuated. So there's quirks of having more dimensions that are not intuitive. And part of what I've been looking at is whether this follows for embeddings as well. So if we assume that our encoders create an approximation of the real world, actually does that approximation get better if you start to apply some of these mathematical concepts around estimators to them? And by and large, I haven't had any meaningful results, at least not outside of any statistical significance. The other thing I've started to look at is optimizations that I can do by region. So as we've talked about, there are multiple points in this cube that behave differently. And if I were to mask them out and plot their loss separately, and these graphs are using mean squared error, so essentially the absolute distance to the ideal value, you can see that actually the regions where most of the coordinates are the same, which is what this one represents. So this one on the left is where all of them are the same. The one on the right is where none of them are the same. And you can see how those 2 graphs are practically inverted from each other for the same training set. And one of the things I've been looking into is how well I can use this inversion to improve or speed up training. And what I've noticed is that at the start, when every single value in that cube is random, then actually it's just the internal diagonal that has any bearing on training. If you think about it, random behavior is perfect for the vast majority of that cube, because what I want is that the 5th item of batch A does not match at all to the 4th item of batch B, and that neither of them have any correlation at all to the 3rd item of batch C, for example. So to all intents and purposes, them being random is a pretty good approximation to that behavior, and they're behaving perfectly. So that behavior I don't actually want to learn from initially, whereas what I would like to see, and what I wouldn't get randomly, is if the 1st item of batch A matches the 1st item of batch B matches the 1st item of batch C. And that's something that I want to emphasize from a gradient. And in my research, I've tried a couple of things, looking at whether I can artificially weight those parts of the graph differently, or whether I can give it a learnt parameter of weights, where if I'm using something like dividing by the norm, so that they can't just learn that if I set all the weights to 0, I get a 0 loss. Whether something like that teaches it well. The idea being that by the time that parameter has learnt to move over to emphasize the parts of the cube where actually the loss is already perfect, I'm hoping that the model's then learned from that diagonal and is starting to need those other parts as reinforcements. And from the results that I've had from that, which hasn't yet been a comprehensive test, but the first few initial experiments have been that it's promising, but syncing those up is really, really difficult, and it's quite an unstable method. So I'm going to talk a little bit now about how I'm actually doing this comparison, because we've talked about the rough ideas behind these statistics and what I want to match in different places, but not actually gone into it. So these are 4 graphs. And on the bottom left, we have cosine similarity and what it looks like in practice. Now, anyone who's familiar with this method will know that it is simply normalized A times normalized B. And that means that you have a vector usually between 1 and -1 that you're just multiplying. And if they match, you get a positive answer. And if they don't, you get a negative answer. And at least that's how it looks like for simple integers. And then when you plot it, that's the kind of heat map that you get. This is what CLIP, the original model, uses, where you're essentially saying, I want the vector output of one encoder to match the vector output of a second encoder. However, when we scale this up into 3 dimensions, this is no longer this simple. What we actually want is a function that matches this cube in the top left, where if all 3 of them match, again, we get a nice pretty heat map in that corner. And if all 3 of them match as negative, we get a heat map in the opposite corner and nothing on the other corners. And this is what I've been working on as a way, because you can't do the intuitive thing of just adding an extra term to cosine similarity. So this heat map in the top left is actually tracking the difference in hypotenuse of the rectangle that is vector A, vector B, vector C, to the hypotenuse of the mean of all those 3 values multiplied together. And I can draw this out geometrically if you want when I'm done. The problem that this poses is this is nice in 3 dimensions, but how do you check for 4, 5, and 6? As I've already said, I can't visualize that in my head, and I wouldn't expect anyone here to be able to. And if you can, please let me know, because it'd be super useful. But this is what I've come up with in the bottom right, which is to say that if I took a diagonal slice through that cube in 3 dimensions, I would get a square. If I took a slice diagonally of that square, I would get a 1-dimensional plane. Whereas if I now do this in 4 dimensions, I get a diagonal slice of 4 dimensions is a cube, and then I can diagonally slice that and get a square, and that's what I've got down here. And this shows the heat map that is going through the diagonal of a 4-dimensional cube. And this way I can check that this heat map actually aligns very loosely to what I would expect for cosine similarity, and I've been able to show that the gradient descent on this does in fact push things to those 2 extreme corners. So this is what I'm currently experimenting with, and stuff's currently running somewhere on campus, trying to check that this model actually behaves under 6 dimensions. So if I go through the results that I've got so far, one of the big things that has come out from this is that balance must be maintained between modalities when using extra dimensions. And what I mean by this is that where I've talked about having an extra encoder in this diagram, I'm actually, for some of my experiments, using the same encoder with just multiple inputs that I'm then laterally splitting up. So if I do not balance these at all and just take the mean of the gradient and then apply it back equally to all encoders, I get a problem where the language learns significantly faster because it has more data, and that's actually quite harmful for the image gradients. So I've had to, in places, artificially adjust that balance by sort of saying, look, you take 1/5 of this gradient, you take the remaining 4/5. The second takeaway point I've got so far is that doing the mean across different regions and across different labels does not have any particular effect on this training methodology, which was odd to me because I expected it to, particularly with what I've termed true labels, which are, instead of using 1s and 0s for use this region, don't use those regions, in the cubes that I've got here, running through some sample values through it and going, these parts of the cube tend to this value in a perfect case, I'll use that as my label as a probability. That has no bearing on gradients, it turns out, which somewhat surprised me because I assumed that if you could tell the model the rough variance it was expecting in each value, I presumed that would help, but it doesn't. The next takeaway point that I've got is that effective logic calculation is sensitive to changes in gradient. If we go back to this graph of different similarity metrics, the difference between bottom left and top right is incredibly significant when you start to apply it to gradients, where you can see the bottom left has quite a steep curve into that corner, and it's much more gentle in the top right, which is actually the function I'm using. In 2 dimensions, this function doesn't behave nearly as well as this one. And that can be quite significant when you then start to scale it up. And I wasn't expecting such a sharp, pronounced difference in these different approaches. My fourth takeaway is quite a simple one. These models only seem to work well when you've got more than 14 layers. You start to get results at about 12 transformer layers, but 14 seems to be the sweet spot where it has enough depth to the network to start picking up the oddities of language and everything in an image. The fifth one we've already loosely talked about, where weighting by region varies over training and cannot be easily learned, which is to say that actually as you go into more than 3 dimensions, the number of different behaviors you have in that cube is not something that I think can manually be trained just based on the number of parameters you'd need. It would be too complicated to sit down and work out the maths for a human, I reckon. Maybe some super boff in here could do it. I certainly can't. Where just because of the number of regions that start to explode, I think in 6 dimensions you're up to 21 off the top of my head, different behaviors that you'd expect in that cube. And that's from things like, I've got 5 out of 6 coordinates matching, I've got 4 and the 2 do or the 2 don't match, I've got 3 and then within that other 3 there's a 2 and a 1, or there's the other 3 match or none of them match, and so on and so on. Lots of different combinations, and trying to manually adjust those according to what you think the model needs is really difficult. However, the big takeaway that I have got is that clip models can be fine-tuned within a few days according and seemingly correlating to the number of logics that are present. And this is really significant because the original model, I think last time I sat down and worked it out, took about 33 GPU years. Or if you're doing it at the scale they're doing it, you can have 512 GPUs churning away for about 3 weeks, and you get your training in a reasonable amount of time. However, as many of us will know, at a university, you don't have access to 512 GPUs, and if you're lucky, you can normally swing 1 or 2. So being able to downscale this to a sensible size, or at least get it within a single GPU's amount of training, where within 3 or 4 days I can fine-tune a model on a data set, is really significant. And adding to this, because again, university scales are different to enterprise scales, the data set that I've been using is every single split of MS Cocoa, which people know is image to 5 captions, give or take. And I've looked at that and gone, oh, well, there's my 6 dimensions, nice and easy. The other positive quirk is that I know that this data set sits in about 200 gigabytes of memory, which again is more than average for most workstations, and it sits well within the remit of what most researchers can wrangle. So it's a really exciting result for me to be able to show that in having lots of different ways of shuffling this data and passing it between different encoders, I unlock the ability to start to generalize language a lot better from such a small amount of data compared to the many, many, many terabytes of web scrape data that were originally used. However, I would add that with the caveat of if it's not in the training set, I can't expect the model to know it, which starts to really apply when you have smaller data sets. But this really opens up the avenue for future research and an emphasis on having multiple correlated points within a data set, as well as starting to look at different ways to scale that. And as this applies to low resource language, which is the way this is, I'm hopefully trying to push this research, it's much, much easier to find data from social media or even though you're trying to manually source the annotations, where you just say caption an image, which is often you get a lot more varied response than having to manually translate stuff and make sure it's a gold standard annotation and whatnot. So hopefully, yeah, this will go somewhere and really open the door for getting other languages on board and more evenly represented within the AI and natural language space. So that roughly brings me 40 minutes into the end of what I've prepared. Thank you very much for listening, and I welcome any questions. If there's anything you want me to expand upon, I'd be absolutely delighted. And really sorry, this has been a very vague whistle-stop tour through everything. Yeah, any questions?
Yeah, fantastic. Thank you very, very much, Steve, and thank you for a very wonderful talk. We've kept to time, so we have room for questions. If there is any question coming in, please feel free to either unmute yourself and ask or put it in the chat. While we wait for people, I just want to ask you a quick one while we wait for other people to ask. Just to confirm, so far you've been playing with the MS Coco, right? And the images to text and text. Have you, I know you probably haven't done that, but have you considered the complexity this method will introduce if you include other modes of data like audio and video and so on? Have you thought about that, or have you explored that in any way?
I've not explored it too much. However, from what I've read of other approaches, there's a lot of ways of doing this. So some of that is just I've not got the spare compute power to suddenly store an extra modality of video and whatnot. But there's a really interesting repository that can be found online looking at applying multilingual BERT models just straight into this, instead of training it as a whole pipeline, which is what the CLIP model does, where you give empty weights to your encoders and then start training. It looks at learning just the projection from a pre-trained model into that cube. And that could be a really interesting avenue when starting to add those other modalities, because it means that you don't have to train everything in one pipeline. The problem with that is that I haven't seen any research into the multimodal activations that you get from this pipeline starting to play out in other modalities that are trained like that.
Yeah, that's also what I think. I think it might actually be a lot more complex as you scale it up to that level. But yeah, it's quite interesting. Yeah, is there any other question? I don't want to dominate this discussion. Yeah, Paul, thank you.
Yeah, this might be a very silly question because my brain's not entirely up to speed yet. First day back in the office, but so I kind of misunderstood or didn't really kind of get what you were saying about when you transition from 2 dimensions to 3 and beyond, and you're explaining with the normal distributions on X1 on your drawing why that's more difficult. And I guess similar point to where you're talking about cosine similarity beyond 2 vectors. So I hadn't looked at that before, just Googling around that. There are ways to do that already, which you presumably have looked at. So why is it inherently, when you're switching from 2 to 3, what's the jump I'm missing somewhere?
So if you think of what happens if we just draw a truth table of 1, 0, -1, 1, 0, -1 for 2 dimensions, actually the products that we get from those are, for this pair, we get 1, we get 0 here, and we get 1 here. Excuse the fact that I've just in autopilot put -1, getting ahead of myself.
All right.
And again, on the diagonals of here, we get sort of lots of zeros when we start doing those cross multiplications. Yeah. Whereas if you have 3 terms in here, and you again do that same product of doing a product vertically down that table, this becomes -1, despite all three terms being similar.
Right.
So that's the base level of why it just doesn't behave correctly. One of the early experiments I did was there's a wonderful function in PyTorch called einsum. And what this lets you do is it lets you just say the shapes of tensors that you have and the output shape you want. So what you can actually do is you can say, if I've got encoder A and it's got shape F, or it will read this as batch times feature space as the output of an encoder. I can then specify BF, CF, DF, EF, and I've already used F, so let's go for GF as well. And I can literally pass it this as a string and say I want the shape A, B, C, D, E, G out, and then I give it these 6 tensors.
Right.
And it does this multiplication and summing along the feature space for you. And what I was finding is that this just does not converge at all, because there is nothing that forces dissimilar items together. And I can further expand this by saying, if you have 4 terms in here, suddenly you can get 1 as the output in this column, but I don't know whether 2 or more are -1.
Right.
So that becomes quite a big problem as you get more and more terms where you just lose the gradients in that calculation, because the model doesn't know which way to push items, and you can get really big variance between what should be very similar vectors based on this.
Okay, got it. Thanks. That was great explanation.